Distributed paradigms. A deep dive into concurrent search techniques. The landscape of search algorithms has evolved dramatically with the rise of distributed computing architectures. Modern applications demand faster data retrieval across massive datasets, pushing traditional sequential methods beyond their limits. This exploration delves into the specialized realm of parallel search strategies designed specifically for concurrent execution environments. In today's computational ecosystem, where multi-core processors and cloud-based infrastructures are ubiquitous, optimizing search operations through concurrency becomes not just beneficial but essential. These techniques redefine how we approach information retrieval in complex system landscapes. Fundamental principles of parallel searching. At its core, parallel searching distributes workload across multiple processing units to achieve faster query resolution times. By leveraging concurrency principles, these approaches can process different segments of data simultaneously rather than sequentially. This distribution often involves partitioning datasets based on various criteria such as spatial proximity, numerical ranges, or categorical groupings. Effective partitioning ensures balanced workloads across all available resources while minimizing communication overhead between them. Data partitioning. Dividing dataset elements according to structural characteristics enhances processing efficiency by reducing internode dependencies during computation phases. Load balancing ensures uniform distribution of tasks among worker nodes, preventing resource underutilization and maintaining consistent performance metrics across all components. Synchronization mechanisms. Coordinating results from parallel executions requires careful synchronization protocols to maintain correctness. Without introducing excessive latency, the choice of partition strategy significantly influences both time complexity and network bandwidth requirements. Hash-based partitioning offers fast lookup capabilities but may introduce uneven distributions depending on input variance. Classifying concurrency models in search optimization. Three primary models dominate contemporary implementations of parallel search algorithms: task parallelism, data parallelism, and pipeline parallelism. Each model presents distinct advantages and trade-offs suitable for particular application scenarios. Task parallelism focuses on decomposing individual search operations into smaller subtasks that can execute independently across different cores or machines. This method shines when dealing with heterogeneous query patterns requiring varied processing pipelines. Data parallelism divides the dataset itself into portions processed identically by multiple workers. It excels in homogeneous search tasks where identical operations apply uniformly across all elements within the partitions. Pipeline parallelism arranges sequential stages of computation in a fashion, allowing continuous processing flow even as new requests arrive. This model is particularly effective for batch processing operations requiring staged transformations before final result determination. Performance characteristics of parallel search implementations. Evaluating performance metrics provides crucial insight into selecting optimal parallel search configurations. Key considerations include speed-up ratios, scalability factors, and fault tolerance mechanisms inherent in each approach. A critical metric for measuring effectiveness is the speed-up ratio, defined as T1/T(p), where T1 represents sequential execution time and T(p) denotes parallel execution using P processors. Ideal linear speedups indicate perfectly scalable solutions free from bottlenecks. Scalability analysis reveals how efficiently systems handle increasing numbers of processors relative to problem size growth. Well-designed implementations show superlinear scaling due to reduced cache misses and better memory utilization at larger scale levels. The fault tolerance mechanism determines resilience against hardware failures during execution. Replication strategies combined with checkpointing ensure continuity despite partial node losses impacting overall workflow integrity. Common data structures utilized in concurrent searches. Selecting appropriate data structures plays a pivotal role in determining concurrency effectiveness. Certain structures inherently support parallel access patterns more gracefully than others. B-trees and variations. Their hierarchical structure allows simultaneous read operations along different branches with minimal contention. However, write operations require careful management since modifications typically affect entire subtrees. Huffman trees and other prefix-encoded variants, optimized for single-threaded querying, these structures suffer from increased lock contention in multi-threaded contexts unless carefully modified with fine-grained locking mechanisms. Binary indexed trees, Fenwick trees, while efficient for range queries in single-threaded settings, they present challenges in concurrent environments necessitating atomic update operations and sophisticated version control schemes. Skip lists offer probabilistic balancing features useful for implementing approximate nearest neighbor searches in distributed settings. They benefit from relaxed consistency requirements compared to balanced binary search tree alternatives. Radix trees provide compact representations suitable for IP address routing tables and similar use cases requiring radix-based lookups. Special attention is required in shared memory implementations to prevent race conditions during updates. Implementation considerations for multi-core architectures. Developing parallel search algorithms for modern CPU architectures introduces several technical challenges related to thread management and memory hierarchy optimization. Coarse-grained versus fine-grained threading choices determine granularity levels affecting context switching costs and potential for pipelining optimizations within instruction streams. Fine-grained approaches offer higher concurrency at expense of additional bookkeeping requirements. CPU caches pose significant optimization opportunities through careful consideration of data locality. Access patterns must align with cache line sizes to minimize unnecessary transfers between registers and off-chip memory components. Memory barriers and fence instructions become essential tools for ensuring correct visibility of updated values across threads. Proper ordering guarantees are crucial for maintaining referential integrity throughout extended computation sequences. Design patterns for distributed computing environments. Distributing search tasks across geographically dispersed nodes requires addressing fundamental concerns regarding network reliability and transmission latencies. Master worker frameworks provide simple yet powerful abstractions enabling flexible coordination between central control points and autonomous worker entities executing localized computations. MapReduce paradigm simplifies development of large-scale distributed programs by abstracting away many implementation details while retaining sufficient flexibility for custom logic specification needs. Consistent hashing techniques enable elastic scaling properties by distributing hash ring placements according to cluster dynamics rather than fixed pre-assigned locations. Replicated state machines ensure availability and persistence characteristics through redundancy provisions even amidst arbitrary node failures affecting ongoing computations. Practical applications and real-world scenarios. Parallel search algorithms find extensive deployment across diverse domains ranging from enterprise databases to scientific research applications. Identifying common use cases helps reinforce theoretical understanding with tangible examples. Search engines implement intricate indexing strategies optimized through parallel sorting and document ranking procedures. Inverted index creation processes benefit immensely from parallel merge sort. Implementations distributing load evenly across all available resources. Scientific simulations utilizing Monte Carlo methods rely heavily on random sampling techniques accelerated via embarrassingly parallel implementations capable of handling millions of independent trials concurrently. Fraud detection systems analyze transaction records using complex rule sets requiring near real-time pattern recognition abilities enhanced through distributed stream processing paradigms employing windowed aggregation functions. Biological sequence alignment projects leverage genome sequencing data processing through parallel string matching algorithms facilitating rapid identification of genetic similarities across vast sequence repositories. Challenges in design and implementation create a robust parallel search implementation demands overcoming several obstacles stemming from conflicting objectives between scalability goals and correctness constraints. Ensuring data consistency remains one of most challenging aspects when coordinating updates across multiple concurrently executing threads operating upon shared mutable states. Synchronizing access to frequently updated metadata fields often introduces measurable delays impacting perceived responsiveness rates of end-user-facing interfaces dependent upon timely query resolutions. Minimizing false sharing effects caused by adjacent memory accesses occurring simultaneously in different threads proves critical in maximizing cache utilization efficiencies, especially for densely packed structures containing small-sized objects. Optimization strategies and best practices tuning parameters correctly is vital towards achieving desired balance between competing factors including throughput volumes, latency bounds, and resource consumption profiles. Implementing proper caching layers reduces redundant I/O operations while providing quicker access paths to commonly requested items, avoiding repetitive computations associated with basic lookup routines. Employing adaptive algorithms enables dynamic adjustments of internal state configurations based on observed workloads, helping maintain stable performance levels regardless of fluctuating demand patterns. Monitoring systems' health indicators regularly helps identify potential issues early enough so preventive maintenance measures can mitigate degradation risks before full-blown failures manifest themselves visibly in production environments. Emerging trends in concurrent information retrieval. Ongoing advancements in computer architecture continue influencing development trajectories of emerging technologies aimed at improving existing search methodologies, further enhancing performance capabilities. Quantum annealing machines demonstrate promise in solving combinatorial optimization problems integral to certain types of graph traversal algorithms used extensively within database indexing constructions. GPGPU accelerators enable novel forms of vectorized processing ideal for kernel-level optimizations, accelerating bitset manipulation operations traditionally performed through software emulation techniques limited by scalar processor speeds. Near-term improvements focusing on heterogeneity-aware scheduling policies aim to optimize resource allocations, taking full advantage of varying compute capabilities available within heterogeneous clusters comprising CPUs, GPUs, FPGAs, etc. Rising interest in self-adjusting data structures capable of reconfiguring themselves automatically based on usage patterns shows growing emphasis toward building adaptivity features directly into foundation layers of storage. Infrastructure designs. Conclusion. The evolution of search algorithms through concurrency and parallelism reflects the ongoing transformation in computational needs driven by increasingly demanding application requirements across numerous industries. By embracing these advanced paradigms, developers gain unparalleled ability to tackle enormous data volumes while maintaining acceptable response time expectations from mission-critical systems relying upon instantaneous query resolutions as essential operational component.